afternoon, good morning, good evening, whenever you happen to be watching this video, and welcome to Lecture 4 of ENGR 2301 Engineering Statics. This will be part 1 of Lecture 4, and in this lecture, in this video, we are going to just go over some brief items on point-particle equilibrium. So let us consider point-particle equilibrium. Point-particle equilibrium. So we touched on this a bit when we looked at 2D equilibrium and when we discussed early on the introduction to statics, looking at how Newton's laws apply to this. But we remember from before that a point particle is one that has all of its mass at one location, or one single dimension, or not really one single dimension, one single location, enough that we can ignore its dimensions. So basically we take an object, a real object that actually does have dimensions, and we compress it down to a single point for analysis. Just another one of our engineering models. And so, again, we can use the point particle assumption in a few cases. Let's see, when can we use this? In a few cases. Some that come to mind, one, when a single point of interest can be cut out and analyzed of a larger frame or a larger object. A tiny piece of an object is useful to analyze. And what comes to mind here is things like ropes, joints and trusses, joints in, or locations where ropes meet up. We saw that before. And also when you've seen this kind of system where you had the multiple ropes hanging down, or if you have any kind of cables or tethers, you might cut out a piece of that, or its intersection where it meets an object, a rigid body, or trusses. We'll get to that later in the semester when we look at truss theory. When we look at trusses, we will isolate a single joint in the truss, and that joint will be, or by a joint I mean where multiple members of the truss meet together, and that joint is then modeled as a point particle. Two, when objects are simply very small. So if we actually do have an object that is very small relative to its surroundings, I should say. Subatomic particles come to mind, but even in cases of some things, basic objects, things like that, when they're small relative to their surroundings, sometimes you can use the point particle assumption. And three, the really big one is when rotational forces are negligible or non-important. Or we are not concerned with rotation. So, for example, if I model the flight, imagine if I take a paper ball, a wad of paper, and I throw it through the air, and I want to model where it strikes the ground using projectile motion. Well, if I am just modeling its height, its velocity, its distance from launch point, that sort of thing, I don't really care how much it rotates as it flies. I'm assuming air resistance to be 0, so the orientation of it really doesn't matter. And so at that point, if I don't care what angle it lands at, or not, I shouldn't say what angle, like in other words, what part of it hits the ground first. I should probably say something like that. If I don't care about its orientation when it strikes the ground, then in that case I could just model it as a simple point particle. Same thing with any rock or any kind of small object that simply can tumble through the air fairly easily. But where we're going to use this most often in statics is cases more like this, where the first case here, when a single tiny, actually there should be a point there. A single tiny point is useful to analyze. Okay, so, and again, the key distinction between rigid bodies and point particles is that rigid bodies have important dimensions or have non-negligible dimensions, while point particles do not. So again, because point particles have all their mass at one location, or have all their mass modeled as one location, we can neglect rotation and rotational forces applied to them. Rotation and thus rotational forces are neglected. And this is the big one. You see, okay, let's consider this. When I use examples of things that are clearly moving, like balls flying through the air and wads of paper and rockets and things like that, you may think to yourself, wait, why are we learning about this? What does this have to do with anything? This is statics class, and by definition, statics things tend not to be moving very much. Well, consider something like a building. If we have a great big building, or a large building, or maybe not even a large building, consider a building with several stories. And I'm going to use an example of seismic design, which is definitely beyond the scope of this course, but it still can serve as a useful example. A building is static. A building, well, hopefully relatively static. In most times, anyway, the building is relatively static, but there are certain times when the building moves. And one of those is under wind loading, and another one is under seismic loading. Now, where we are here in Texas, we don't tend to get a lot of seismic loading, but in other areas, we definitely do. Other areas of the country, we definitely do. And one of the, now again, this is not a course on seismic design, but one of the major aspects of seismic design is something called overturning moment. So if the ground suddenly moves rapidly this way, the building is going to have a tendency to kind of rotate over like this. And you actually have a rotational force, not just a lateral force, but actually a torque, a rotational moment that wants to tend to cause this building to fall over, not collapse downward and not snap at its base in shear, but actually overturn. And that's a moment so that basically this side, if it wants to go like this column here is going into tension and this one's going into compression. It's undergoing an overturning moment. And we'll learn about what moments are next week. But the reason I'm giving this as an example is that just because something is stationary or can be modeled as relatively stationary doesn't mean we're not concerned with rotational forces. So the whole idea of modeling this rotational force is that you're actually trying to prevent it from moving. You're going to say, okay, well, what kind of we know it wants to rotate under these forces, but how much what kind of strength do we need to have in the legs here in order to prevent it from falling over? And so often in civil engineering, at least, when we're looking at moments, we're saying, okay, what kind of forces do we need to prevent rotation? And same thing in statics. We're saying, okay, yes, this is not a dynamics problem, but what kind of forces do we need to apply to prevent rotation? So, and the same thing is basically with point particles. So we're going to apply forces. We're going to apply different forces to things, and we're not going to be calculating accelerations, but we are going to be looking to calculate what kind of forces need to be present on an object in order to prevent rotation. So again, we don't need to worry about rotational forces. That's not a problem here. So we're not doing anything like overturning moment, but we are going to have a variety of forces applied to particles. And so in turn, the equations for equilibrium for particles will be as follows. Equilibrium for point particles. And I'll do this in 3D. So let us consider you have a three-dimensional space, x, y, and z axis, and z. And let's say I have a point particle, just some particle, maybe maybe I can call this particle A or something. And let me then show a variety of forces applied to it. So maybe I have F1, F2, F3, and F4. So each of these would be a full force vector like we've seen in lecture 3. And they'd each have their own x, y, z components, their own magnitudes, their own unit vectors, etc. F1, F2, F3, and F4. Now, so in order for this to be in equilibrium, all of these forces must be in balance. And what does that mean? Well, does that mean that, let's think about that. Does that mean that we could just add them together? What does balance mean? Does that mean that f1 plus f2 plus f3 plus f4 is 0? Is that what we mean? No, that's not what we mean. Unless we're talking about a vector sum. If we're talking a vector sum, adding the actual Cartesian vectors together, f1, f2, f3, f4, if you want that to equal 0, yes, then in that case, that's what we were talking about. So, and again, all of this is coming from Newton's second law. Remember, the sum of forces is equal to mass times acceleration. And if we are fixing the acceleration at 0, we will say the sum of forces is equal to 0. And in particular, we'll break that down into a sum of forces in the x direction, a sum of forces in the y direction. Oh, missed my f there. A sum of forces in the y direction, and a sum of forces, let me put that over here, and a sum of forces in the z direction, or z if you prefer. Alright, so we have that. So now let's look how we would apply this in our system here. So if I want to do a sum of forces, let's see here, in the x direction. Well, I will say the f1 in the x direction, plus f2, its component in the x direction, plus f3, its component in the x direction, plus f4, its component in the x direction. All of these must come to 0. So we will then equate the individual x components of these in order to get a final result. And usually this is not the final thing we're looking for. Often this is, depending on the problem or depending on what you're designing or analyzing, sometimes this is just one step. You don't just set forces up and then prove they're equal to 0. You often are looking for some relationship between one of these and another or something like that. Sum of forces y. That's going to be f1y plus f2y plus f3y plus f4y. And you can probably see where this is going. That's equals 0. And sum of forces in the z direction will be f1z plus f2z plus f3z plus f4z. Now, this is certainly getting a bit repetitive, but just wanted to write it all out for the sake of completion. So, in other words, the individual forces do not add up to 0, and their individual magnitudes don't add up to 0, because that wouldn't even make any sense. But their x components add up to 0, their y components add up to 0, and individually the z components add up to 0 as well. Okay, and that is the basic idea of point-particle equilibrium. So, I think we will look at this. That is the basic theory of it. I think that'll conclude for part 1. Let's do a short part 1 here. In part 2, I plan to look at the nature of free body diagrams and the process therein, and we'll look at some other things in a part 3 and possibly part 4. All right, that'll do it for now. I'll see you soon for part 2, and as always, thank you.